This is joint work with my colleagues, most of who are here. You can get further details on our work at our website. I'll give a brief introduction over our approach because it's a little different from the traditional approaches to infection propagation. I'll briefly summarize prior results and then update you on more recent results since the last Blue Waters meeting. Air travel is an important factor in the spread of diseases. And every time there's an epidemic, often there's a panic and people call for ban on air travel and stuff like that. But it has a huge human and economic impact. So it is best to try to mitigate the spread of the disease rather than take drastic action like banning flights. It reassures the public that action is being taken. At the same time, it avoids the negative human and economic consequences. Our project goal is to develop models and a decision support infrastructure in an actual decision support environment, and which will provide insight to policymakers on what are the suitable decisions to take, what are possible consequences, and so on. Our original work focused on Ebola, but we are currently extending it to other diseases. This is a sample of a prototype of decision support infrastructure. Currently, most of the models are based on scientific application rather than policy analysis. For example, they may try to do better prediction of how diseases are transmitted and so on. But inherently, there are a lot of uncertainties, especially in the early stage of a disease. So it's really impossible to do prediction. So our approach is to say, what do you really need in a decision support environment to take suitable decisions. Also, it is based on current models are based on aggregate analysis. What we look at is we look at more fine-scale model of human movement, because aggregate analysis basically says how diseases spread given current interaction patterns between people. But if the interaction pattern changes, then the likelihood of spread of diseases also could change. Okay, so our idea is, through some fine-scale policies, can we change the interaction patterns of people so that the disease is less likely to spread while maintaining the same aggregate passenger traffic? Okay. And we link this fine-scale model with a genetic and geographic model called phylogeography to look at the global consequences of decisions taken at the local scale. We deal with uncertainty by parameterizing the sources of the uncertainty, and then we do a parameter sweep over this space to identify vulnerability. Our goal is not to predict what is going to happen, because that's pretty much impossible. And instead, we'll say that a policy is robust if under the many different scenarios that could take place, it always gives decent results. So its expected value may not necessarily be the best, but it is the most robust among all the policies. So here's a flowchart which gives our approach. We may have different procedures, for example, different boarding procedures, or maybe different airport layouts, and see how does that impact movement of individual passengers. For example, how does the boarding procedure impact how they move within the plane? And based on that, we get Ebola. We start off with Ebola, which is a contact-based disease. And basically, we're looking at diseases that are based on proximity rather than something where the airborne infection can travel long distances. So we look at a number of contacts, or basically are people coming very close to each other. And based on that, we predict the number of infected people using a susceptible infective model. And this information can be, we can calculate the number of infectors per airport, and then feed it to a phylogeography model, which can use this in addition to genetic information to look at the global spread of disease. In today's talk, I will focus mostly on this aspect of the problem. So we can ask some questions such as, does air travel pose a big risk of the spread of diseases? Can we disrupt, can we reduce the likelihood of infection by, for example, changing plane type, changing boarding or disembarkation procedures, changing seating arrangements, and so on. I'll briefly summarize prior results. Basically, our model for passenger movement is the self-propelled entity dynamics model. It is basically like molecular dynamics. The main difference is that each human is treated like a particle, but of course there's no attractive force. Instead of attractive force, there's a self-propulsion because they want to go to a desired place. For example, if they are leaving the plane, they want to go to the exit. If they are boarding the plane, they want to go to their seat. So that's a self-propelling force, and that's a counteracting force that repels them. That is, you don't want to get too close to someone, or you don't want to go into a wall or something like that. Okay, and then you integrate using Newton's law of motion to look at the new position of each person and velocity, and you iterate over this, so you can find out where each person is at any moment, and later at a analysis stage, you can see who got close to someone else. We are assuming we don't know who's infected, because if you knew someone who's infected, they would probably be quarantined. So we are looking at that as one of the sources of uncertainty and unpredictability. And we look at each scenario for who could be infected. So there are other sources of uncertainty. For example, the average velocity at which people move varies a lot. So that's another source of uncertainty. And we have many different parameter combinations. For example, in a simple simulation, we have about 5 different sources of uncertainty. If we do a sweep over that, we can get many different results. And some of those are unrealistic in terms of the time taken, or they may be unrealistic in terms of the pattern or qualitative pattern of people moving. So we eliminate those, and we choose a subset of patterns where we can, which look somewhat realistic. So this is an example of a simulation of boarding. You can see we basically track how each passenger moves into a particular seat. And based on that, we can see who got close to whom in the process of boarding the plane. Based on that, in the last Blue Waters Symposium, we estimated the number of contacts between different people. And what is the contact? Well, we may say it's maybe it's perhaps 1.5 feet, perhaps it is 3 feet. So we look at different scenarios for that, and again for 2 different plane types. The general idea is that this suggests that random boarding, like maybe sometimes Southwest does, gives you a fewer number of contacts, and you would hope that a fewer number of contacts would translate to a smaller number of infections. Generally, it turns out that things that strategies that are effective for moving people into a plane are also effective at transmitting diseases. Okay, so and if you want to avoid transmitting diseases, you should be willing to pay a price of not boarding as fast as possible. We suspect that most people would prefer to board 2 minutes later than acquire Ebola. So we also did some workflow optimizations in terms of the computation and some basic sequential optimizations, and we could reduce the time taken by a factor of 10, and on the 1,331 cores. We also did some I/O optimization, which reduced the wall clock time by a factor of 2. You can see here that this is a histogram of time taken by different processes. You can see there's a wide variation. So this suggests that there is a lot of scope for load balancing. So we did some load balancing, and on about 40,000 cores, we were able to get time within 10% of the time taken on 68,000 cores if we use 1 core per process. So this was some stuff we had done last time. I will give you more recent results dealing with the infection propagation. Generally, Ebola is not very infective. The average person spreads it to only 2 other people, whereas something like SARS, an average infected person spreads it to about 4 other people. But this is a coarse scale model that assumes a certain the existing interaction pattern of people. What if it changes, right? So we have a probability model for infection transmission, which models it as a function of the distance to an infected person, exposure time, and infectivity of the person. Now, for example, if you have a certain disease at different days, your infectivity actually varies. So based on the virus count in the blood, we developed the probability distribution for the likelihood of infection transmission at different days. You can see this is around the peak, but there is some infectivity even a little later. The profile for SARS varies a lot, and even after a long time, there's a reasonably significant likelihood of infectivity. So this is the impact of the boarding strategy. This is random boarding. So you can see that we are especially interested in what happens at this end of the spectrum, because we want to avoid high-risk scenarios where a lot of people get infected. And you can see that the random boarding has substantially lower infectivity than other boarding strategies. For example, if you have 3 sections, like let's say 3 zones, okay, then we have this scenario out here. We looked at a few other strategies too, and it looks like the random boarding does the best. And the reason it does the best is it reduces clustering in the cabin. If you have zone-wide boarding, a lot of people tend to be putting their luggage and all that at the same time in the same place. By the way, I should clarify that our model, apart from the molecular dynamics type stuff, it also has some behavioral features, for example, to account for how people put stuff into the luggage compartment. And generally, people are reasonably civil when they're deplaning. You know, they let people in the front row leave before they go in and so on. So there are a few behavioral features too. And we then looked at deplaning. We saw the number of contacts, we can make a substantial difference. However, in terms of infection propagation, it turns out that especially at the higher end, there's really not much of a difference between all these strategies. Also, one thing I should caution you is that, as I mentioned earlier, we are not doing prediction, So when we say, for example, this is the probability of 2 people getting infected, it's not exactly that we are predicting that 2 people are going to be infected, because there are some sources of things that are not known, certain a priori probabilities and so on. Rather, it is meant to compare different strategies and identify the causes of why different strategies lead to different outcomes. Okay, so basically what this says is that qualitatively, these different strategies differ in a particular manner. Okay. Now, this is the impact of infectivity, because different diseases have different infectivity, and the same disease on different days, they have different infectivity. This is again for Ebola. And so the contact radius at which you can get infected is 1.2 meters, correspond to Ebola. And at different days, you can see that you have very different profiles on the infectivity. Okay. So for example, in days 1 or 2, you are very not likely to lead to a lot of big number of infection cases, and a lot of symptoms are not very well developed either. So let's say you want to do some kind of a screening to determine if people are infected people are boarding the plane or so on. Then you may say, okay, in certain days over here, in this range of days, people are more likely to spread the disease. So let us target screening for symptoms that are displayed at in those days or so on. Then this is the impact on plane size. I should remove this. This is not just the Boeing 757. We have a variety of planes. Again, this is for Ebola, and basically the moral over here is that if you have a smaller plane, then you have much less likelihood of people being infected. The large planes generally tend to have a bigger tail out here, where more people are likely to be infected. So small planes are better than big. However, implementing this in practice might be a little difficult, because let's say we have 300 people. It may not necessarily be feasible to have 2 different planes carry them. But this is some result that is available in case policymakers could find a way of implementing it. This is the impact of contact radius. Again, different diseases have different contact radiuses. Ebola is contact-based, so it spreads through coarse droplets that don't travel far, whereas SARS and H1N1 have smaller particles, so they travel farther away. And you can see that generally things that are have a small contact radius, of course, lead to less likelihood of infection transmission. It also gives you a qualitative idea of what diseases, if a new epidemic comes in, then you don't need to redo all the computation. You could figure out, well, you say, okay, this new disease is in this range, so maybe we need to be very careful, or maybe you would say, well, the new disease is in this range, so we don't need to worry too much about air travel. Maybe we don't need to come up with bans and stuff like that. Now, this is an example comparing Ebola with SARS, just to show the difference between long and short. And we look at Ebola day 1 versus Ebola peak. Okay, so you can see that in Ebola, that's kind of a maximum over which it doesn't really go much. And that is a noticeable difference. If you're looking at this, there is a substantial difference between the peak and the first day. Whereas in SARS, both the situations, day 1 infection and peak infection, are both having substantial infection probability, unlike Ebola. If you look at the deplaning, then you see that there's not really much, the number of passengers again is much fewer, and you don't have as much difference between the two diseases as you had out here. And in general, it turns out that boarding is a more significant factor in the spread of diseases than disembarkation. If you look at the exact detail, the probabilities here are substantially higher than what we had earlier, because this includes airport gates also, both in deplaning and enplaning. However, in deplaning, the airport gates really don't make much of a difference. In boarding, the airport, what happens in the gate, from the gate you go all the way to the seat, that whole process actually makes a substantial difference, not just what is happening in the flight. Okay. So which suggests that you need to do something about what is happening in the gate also, not just change the boarding procedure by saying we'll have random boarding, but look at what is happening at the gates too. Okay. So in conclusion, in terms of the computational optimization, we reduce the time taken substantially, and the number of processes also substantially. We can further reduce it if we have good runtime prediction, because it'll enable us to use optimum. But again, optimum it's an NP-hard problem. So optimum means it'll allow us to use a better load balancing algorithm, which will allow us to reduce the number of codes used substantially. In terms of the application result, we identify policies that can lead to significant decrease in a number of contacts. The important thing is we identify that boarding is a big dominant factor rather than deplaning, and it also has a random boarding leads to a reasonably lower likelihood of infection spread compared to traditional zone-wise boarding. Okay. Also, we found that smaller planes are better than larger ones. In future directions, we are extending it to other diseases. Some diseases are a little bit more difficult because they're much more airborne than Ebola. We are also extending it to airports. Right now, we are looking at gates. We also plan to look at some different regions, for example, a few restaurants or baggage claim and so on, where people tend to accumulate. We'll look at better runtime prediction and more efficient parameter sweep using some ideas that actually I think are similar to what the previous speaker actually presented in terms of identifying regions of parameter sweep that are giving similar results to already calculated ones. Our eventual goal is our current computation time is about 20 minutes. We want to reduce it to about 1 minute, because then we can actually use it real time in a decision support environment, where if someone suggests a new policy to evaluate, we can actually evaluate it and give the result. Because right now we can only do it offline, because if someone suggests a policy and we wait 20 minutes, then the conversation has actually moved on to different direction, which will require finer scale parallelization rather than a more kind of embarrassingly parallel type of parallelism that we have done right now. Okay. So I guess I have a couple of time for questions, or minutes for questions.